Well, so very good morning, dear students, respected teaching community, and all science lovers sitting in front of the screens. Yes, this is a bright morning, and I, Govind Lakhotia, welcome you all for 11th Weekend Science Stories via this virtual platform of Bajaj Science Center. Through this platform, we are trying to explore some hidden spectrum of science, and we feel proud to host great minds of this country. Last Sunday, we came to know about the Newton and his contribution to the society by Dr. Anvesh Mozumdar from HBCAC, TIFR, Mumbai. Today's session will take you to the world of astronomy. And for this, we are fortunate to get the time of Dr. Dipankar Banerjee, who is currently serving as a director of Aryabhat Research Institute of Observational Science, which is an autonomous institute running under Department of Science and Technology, located at the hill station Nainital in Uttarakhand. Before joining this National Institute ARIES in December 2019 as director, Professor Banerjee was working as professor in, I mean, he is associated with Indian Institute of Astrophysics, that is IIA, again a national institute which is there in Bangalore, where he joined as a scientist way back in the year 2004. IIA is his alma mater, from where he has completed his doctoral studies also, and went on to UK and Belgium for more than 7 years for his postdoctoral studies. During his long journey, he has published more than 100 international research articles in reputed journals. His research interests includes multi-wavelength study of solar atmosphere using ground and space-based instruments, diagnostic of solar atmosphere using atomic spectroscopy, providing observational constraints for solar wind and space weather, magnetic seismology, imaging and spectroscopic instrumentation, study of the long-term variation of sun using Kodaikanal and other digitalized archive, space climate. With this gigantic knowledge, he is associated with number of national and international bodies. His other interests are very interesting to listen. He is avid follower of all sorts of sports and was the part of IASC football team also for 5 years. He has trained himself in Hindustani vocals also. He was the president of Bangalore-based Bengali theatre group. With all due respect, I welcome Dr. Banerjee for today's bright talk on the stories of sunspots and solar cycles. Before I request Professor Banerjee to begin with, I'm informing every listener on YouTube that the chat box is disabled and it will be enabled at the end of the talk. So you can write down your queries in between, and at the end you can text your questions for the interaction with your names and class. So I request Professor Banerjee to start.
Good morning. Thank you very much for providing me this platform. Yeah, I would love to, see the young minds face to face, because unless you look at their eyes, you can't really make out that whether your message is, getting transmitted. But unfortunately, because of this current situation, we have to take resort to this virtual media and try our best to convey the message which we want to. So again, thank you very much for your generous introduction. It's not so important for most of the people, but I would love to, interact with the students and see if I can excite any, an excitement in terms of the science and the kind of things what we do. So today's story is about sunspots. So I will try to tell you what are these objects, and also we'll try to connect with a little bit of history. I hear that you heard about Newton, and so I will start from Galileo Galilei today from that. Before I get into the subject, I thought I will let you also know where I am at this point of time. It's a pretty place. The two images what you see here, the top figure belongs to Manora Peak, and I'm actually sitting in this circle somewhere in this part, which is 10 kilometers south of Nainital city. But the Aryabhatta Institute has also another campus called Devasthal, which is about 50 kilometers east of Nainital city. And that's a more modern observatory what we have, and that is hosting the India's largest optical telescope now. So again, I would love to host you here sometime in near future, hopefully when situation prevails. Please get in touch with Govind. Govind will organize such a trip to these beautiful places around. A little closer view. This is my office here. although I'm in somewhere down below in this hill today, I'm giving this lecture from my home. It's a Sunday morning, pleasant time. This observatory was under the Uttar Pradesh State Department, and it hosted a 1 meter Sampurnanand telescope, and this is still operational from 1972, one of the oldest telescopes in the country of this class. It also hosts a 15 centimeter solar telescope, which is operational from 1993. We look at solar flares. These are very dynamic, explosions which happens in the solar atmosphere. It also hosts a 50 centimeter Smith telescope, which is operational from 2009, here. These are a close-up view of this, 1 meter telescope and the dome. As you can imagine, this is more than 50 years old, but still fully operational and maintained here. And most of our PhD students who are in this campus, they go in the night and they operate this telescope on their own. There is no other technical support. They just go, they open the dome, and they start using this telescope. This is the 15 centimeter solar telescope I was referring to. You can just go up this tower and look at the sun, of course, through this telescope in a computer room downstairs, and observe solar flares. This is our newer campus called Devasthan, which is about 2.5 kilometers above the sea level, which first got this 1.3 meter optical telescope, which is operational since 2010, almost 10 years. And this is the nation's pride, we call it, 3.6 meter Devasthan optical telescope, which was inaugurated remotely by none other than Narendra Modi ji and the Belgian Prime Minister from Brussels, because this is a collaborative effort from government of Belgium and India. We also have a 4-meter liquid mirror telescope, which was expected to get the first light in 2019. We have some challenges. We are expecting to get this first light also very soon. So that's the kind of telescopes which you have. And as you can see, it's a beautiful site. You see the entire Himalayan range in the background. And it's a very, very pretty site, really. And this is the largest optical telescope in the country now, which we are devoting for the study of faint galactic and extragalactic sources. Now let me take you to a journey to the sun. So sun, is our nearest star. It is a very dynamic star. It is very active, always changing. The question is, sun is a very old astronomical object. People have been looking for centuries, but still, it is, not many things we know about the sun. Primarily because, sun emits radiations in all sorts of wavelength. This particular image, what you see, is actually an extreme ultraviolet image taken from a satellite called Solar Dynamic Observatory. And as you can see from this, image, the apparently steady sun, what it appears in the sky, is actually quite dynamic, and often it gives rise to a lot of explosions, and material is thrown into, into the interplanetary space. So here you see an image of a huge explosion, and the region underneath where these explosion happens, which is this bright location, what you see here, is actually strong magnetic field region, and that's the region which is called sunspot underneath. So I will be talking about it mostly today, about that object. So sun is a normal star. It's a middle-aged main sequence star. So you don't have to worry about too much, but you can only imagine that these stars are born from interstellar medium, this void space, what you see in the interstellar medium. But it is undergoing some evolution, and it is in the middle age. Like, all human beings start from a early career, and then it goes under evolution. Sun also is undergoing an evolution. But it is a spatial star because it is the only star which can resolve the spatial scale on which fundamental processes takes place. Means, most of the objects what you see in the sky, you see them as a point object. You really cannot, see the details on the surface of that object. Whereas sun is being closer to us, we are able to see much more detail. So it is very important to understand this object, so that the knowledge what we gain from understanding this closest star, we can extrapolate that for the understanding of the other stars and other astronomical objects. Of course, it is a special star because it's providing all the energy to the Earth. Our existence is because of the presence of the sun at an appropriate distance. You know that. I mean, the other planets are also being discovered in the other solar system, which is called extrasolar systems. But there we do not know whether there is a life and so on, because there are a lot of conditions has to be fulfilled for a life to happen. It also is a special star because it provides a unique laboratory in which to learn about various branches of physics. I will not go into the greater detail today, because I understand the people who are mostly listening to this talk are from the school level, but you are familiar with atomic physics. You are familiar with sort of heard about this nuclear physics. So you can imagine that all these different branches of physics are being tested in the solar conditions, because in the laboratory, in our ground laboratory, we cannot achieve certain conditions of those very high temperature or very low density or very strong magnetic field environment. So to test your theories of physics in those conditions, you need to verify your model somewhere, and that somewhere is actually is providing the sun. So sun is a beautiful astrophysical laboratory as well. Of course, sun is located in the spiral arm of our own galaxy. This is called the Milky Way as well. And there are several arms of these, our galaxy. And this red marks the location in the Orion arm where sun is to be located. Sun orbits the center of the Milky Way in about 200 to 250 million years. And the solar system has a velocity of 230 kilometers per second as well. Our galaxy consists of about 100 billion other stars, and there are about 100 billion other galaxies. So you think about how many objects are there in the sky, and I am only talking about one such object in this huge number game. So be aware, not much is known about this universe, and there's still a lot to be explored, and you guys need to work on these objects as well. Of course, sun has inspired mythology in many cultures, including the ancient Egyptians, the Aztecs, the Native Americans, Indian, Chinese, for centuries. Sun is 333,000 times more massive than the Earth and contains 99.86% of the mass of the entire solar system. Why I put this number here is, you can imagine in a many body problem, there are many objects, and if one object is so heavy as compared to the other objects, so you can straight away feel that the motion of most of the other objects are being mostly controlled by this central massive object, which is the sun in the center. So there are a lot of superstitions and other things you will hear about. If this planet moves a little bit, what can happen and things like that. But be aware that sun controls these motions of all the other the planets and so on, and that's the most important. Within the sun, it consists of 78% of hydrogen, 20% of helium, and 2% of other elements. What happens is, actually this hydrogen gets converted to helium and generates all these huge amount of energy and other particles and so on. And that's the source of all the radiation, what you see coming from the sun. So basically, it's a thermonuclear reaction which is happening right in the core of the sun. So that's a sort of very, very short summary about our nearest star, sun. But now I will take you to the history and this object, what I'm going to talk about for the rest of today's talk. So this again was due to Galileo Galilei. 1610, he started looking at the sun with the just invented telescope, and he realized that these particular dark, incidentally, this animation which is happening here is a movie made out of hand drawing of Galileo Galilei. Galileo was marking this with his pencil, these small little patches on the solar disk. So what we can see with our eye or through the telescope projecting into the image is these dark small little spots on this object. What he also noticed that when he is looking at this object in the next day, it appears that the object has moved towards the right. Of course, this is solar north and this is south. Because of the different locations, you will have an inclination of the image what you record from the ground. So if today sunspot was somewhere here, and then let me go back to this previous slide and just stop it somewhere. So here you see the sunspot was here. Then the next day when he noted, the sunspot has moved. So that means it can only move if that object is actually rotating around its own axis. So it's just not that Galileo first observed, was the person who first observed this particular object called sunspots. Of course, it was not named as sunspot, and he didn't know what these objects are at that point of time. That came much, much later. But he, by following the images of solar disk images, he could make out that the sun is also rotating about its own axis. So this is a very, very important discovery as well. So again, this is the same animation, and there he did indicate that sun is rotating around. So this rotation is a very important parameter for describing what this object is, why these sunspots come in the first place, and so on. Now, if I look at someday in the solar disk with the white light, these are called white light images. If you just take a standard filter which passes lots of wavelengths, and you take image, some days you will not find anything on the solar surface, but someday you will find the image looks something like this. And these are the locations where you see that brightness seems to be slightly less. Something is absorbing amount of energy, and these locations are called sunspots. Now, what are the sizes of the sunspots? It is a comparison of a sunspot region. And as you can see, there seems to be a very deep core in the sunspot, and there are certain periphery regions which seems to have a different kind of structure as compared to the core. So I will not go into the larger details about the physics of the sunspots and why there are different structures and so on. But many things can be studied from this one object itself. So how these sunspots are formed? Now we understand these sunspots are nothing but they're magnetic structures. There are concentrated magnetic regions. And it appears that these magnetic regions are like a balloon or a flux tube. You can imagine about a rubber tube. And if you immerse this rubber tube in a bucket of water, what happens? The rubber tube seems to come up. It comes to float. You know about Archimedes' principle, right? Because anything lighter, it has to come out of the water surface as well. So here it is the same thing. Underneath the sun is actually convective. The energy can be propagated by different processes, right? Conduction, convection, radiation, and so on. So convection is one of the efficient energy process whereby material is churned back and forth, and then energy is propagated. I mean, you take a boil up. If you just take a soup and then you start supplying heat from the lower surface, that means you start boiling, you will see after a time the hot things will come to the top by forming some bubbles, and then the cold thing will go down into the bottom. So that will set up the convection. So in the sun also, that is what happens. So underneath the surface of the sun, there is a convective layer. Within that, this kind of magnetic tube, as you can compare with a rubber tube analogy which I was giving, those rubber tubes come up. So basically, sunspots always comes in also in pair. I will come to this because the magnetic field always maintains a north polarity and south polarity like a bar magnet. So these are the tubes which are coming out, and they pair and form these kind of long tube structures. And eventually these long tube structures can be also twisted, and further then you can have an big explosions, which gives rise to flares and solar storms and so on. So today I will not talk about flares or solar storms, because that's another story in its own right. Today I will only focus on these concentrated magnetic regions which are called the sunspot, which basically connects these flux tubes. So that's the story today. And this is a cartoon picture how these sunspots are formed. Don't have to bother about these equations. This is the surface of the sun, of the sun, which the disk what we see in the white light. And these are the flux tubes which I was talking about. Basically, they come up initially. They stay in the bottom of the convection zone. This say 30% inside the sun, and then these flux tubes come up. They float as because they are lighter compared to the surrounding, so they have to come up. And as they come up, they penetrate the surface, and where the locations where they penetrate, these are the locations of the sunspots. So if you know that much is enough for the rest of the story today. But now there is a history about these sunspots, in the sense, as I shown you in few images back, that some days you have some sunspots, some days you do not have sunspots, and sometimes you have many sunspots. So this is what is called solar cycle. What is shown here is yearly sunspot number for last 400 years. So as Galileo was just doing the drawing for every day, people have been recording these sunspots and noting down. Today I see one sunspot. Tomorrow I see two sunspots. Day after tomorrow I see 5 sunspots. So like that, they have counted these sunspot numbers on the surface of the sun. And if you plot it for all 400 years, you get something like this. So here it is plotted is a year, and this side it is the sunspot number. So what you can see is there seems to be a periodicity. So there is alternating peaks in solar activity. Sometimes there are a period over which there are lots of sunspots. Almost every day you will find lots of sunspots. They are called maxima, followed by quiet period. Then there are only very few sunspots, or some days there won't be any sunspot. There could be months over which there is no sunspot. They are called the solar minima. So the time variation is predominantly cyclic, and mean period is about 11 years. There is also some more things to be noted from here. This is actually the 2 vertical lines is the first regular sunspot observation done by Samuel Swabe. So that's why solar cycle is sometimes also named as Swabe cycle. So what you see here is the amplitude of these variations also vary. Certain period, like now we are seeing, say, around 1957, that was the strongest sunspot cycle in the last century. But it appears that all the subsequent sunspot cycles were weaker, and we are actually entering into more weaker and weaker solar cycles. In the past, the cycles have been much stronger. But there is also another important thing to be noted here is between 1650 and 1700, there were hardly any sunspots recorded at all. What was the mystery? Was the sun suddenly, not producing any sunspot? So this is what, we still do not understand completely. This is called Maunder minima, because the scientist Maunder discovered that there were absence of sunspots, as recorded in our 400 years of history, and this still we are trying to explain. What I will try to do today is try to give you a physical understanding or a physical model, a physics-based model, which will explain this presence of the sunspot. And also there are certain properties of the sunspots, like the sunspots appear on the surface of the sun. First of all, the sunspot, this is an image taken from, again, a Japanese satellite, and you see there is a pair of sunspots, and underneath, if you just want to take a magnetic map of that area, that means you just want to find out where are the locations where you have strong magnetic field. So these are called magnetograms, and what you see here is there is an opposite polarity. So these are the strongest field, but also there what is also to be noted is these two pairs of sunspots, they have an inclination. This is called a tilt. This overall region where the strong fields are, they are called active region. The rest of the sun where the magnetic field is not so strong, they are called the quiet region. This is a historical nomenclature, so I will be using that word time to time. So here you see that the sunspots are there, but they are tilted also. Now, that's a close-up view of a pair of sunspot. But if I look at a period when lots of sunspots or magnetic field is there on the sun, you will see that, in the northern hemisphere, these are the two polarities. But interestingly, the yellow guys are always right of the, green guys. Whereas in the southern hemisphere, this is ulta. So the polarity orientation is opposite in the two hemispheres. So what I'm trying to do first is I'm trying to list out what are the properties of the sunspots we observe. Now, these observed properties has to be explained by a theory. So I will give you a flavor how we do the research. First we collect the, scientific observations, right? Now we have to try to explain these observations. How do you explain these observations? If there is theory which can support this observation, that is the route I'm taking today, and I will try to share with you. So what needs to be explained? This is called the sunspot cycle. The spot positions. So these sunspots, also there is another property, is appears that they, in the beginning of the solar cycle, they appear in the higher latitude. So if you call this as the solar disk, this way it is the latitude. As you go to the higher and higher latitude, this is pole and this is equator. In the beginning of the solar cycle, sunspots appear in the higher latitude, but with the progression of the solar cycle, they appear in the lower and lower latitude, more closer to the equator. And if you can map this again with time, with the periodicity for many cycles, you will find this kind of diagram. And this diagram is called a butterfly diagram, because you see this is very similar to a butterfly. And that is also again repeating every 11 years. So if you again have to have a theory, it should be able to explain these properties which I have said. First is, sunspot always comes in pairs. They come with a tilt angle. They come also, the polarity orientation is different in the northern hemisphere and southern hemisphere. And then this particular feature, that in the beginning of the cycle, they appear in the higher latitude. With the progression of the solar cycle, they go more towards the equator. So that's the property of the sunspot, which we know. I will give you a closer look of some of the observations. These are called magnetograms. Magnetograms means the magnetic map on the surface of the sun. This is again taken from a satellite observations called magnetic Doppler imager on a SOHO spacecraft. And as you see, the magnetic regions are always bipolar, indicated by plus and minus. Again, you see this inclination there, and this is the inclination angle, which is called the tilt. And if you see in the southern hemisphere, you will see the tilt is indicated by this angle. And again, as I indicated, the polarity of the northern hemisphere and the southern hemisphere is opposite. This also has to be explained. Now, these magnetic images, the location of the concentrations of the magnetic field, if you want to create as an animation by combining data from last, say, several of decades, this is the image which you get. See, first what I showed in the cartoon diagram was just the sunspot location. Now we are only locating the region where the magnetic field is there. So through that process, what we'll say that the sunspots are nothing but magnetic field concentration. So this is how again a convergence happens, because independently we were taking sunspot observations by white light images, and then independently we were taking magnetic field observations. And now when we compare a magnetic field observation with white light observations, that gives us a confirmation that whatever you see as a sunspot is nothing but concentrations of magnetic regions, and also there are bipolar regions. So what you see here is that in a certain period, there are lots of sunspots. This is going through a minimum, hardly any sunspot. But again, sunspots appear in the higher latitude, and then you will see progressively they're going to the equator, and then there is a period over which there are not many sunspots. If you translate these information into this diagram, this is what is called magnetic butterfly diagram. There are two other information which is available here as well. So as you can see here, the northern hemisphere in this particular phase during 1990, you have blue guys who are moving to the equator, and the yellow fellas are going towards the equator from the other hemisphere, and they will actually cancel each other when they reach in the equatorial region. And that's how you get the minima, basically, because one magnetic polarity is canceling the other magnetic polarity, and you have a zero field kind of situation. But there is another interesting aspect we need to explain for the solar cycle is, you see there are also these yellow polarities. As you have seen, that magnetic field always come as a bipolar region. So these yellow polarities, they are moving towards the pole. But you see, the pre-existing polarity of the northern hemisphere was blue. So these yellow guys have slowly eaten up those blue polarity, and eventually the polarity of that northern hemisphere has become, yellow altogether. This is called polarity reversal. That means, you think about it, sun as a magnetic dipole, if you can think, this bar magnet gets flipped every 11 years. So you need really a big theory to explain this flipping of the magnetic field. Incidentally, Earth also has a magnetic field, So Earth has also its magnetic field, and it's very important that Earth has a magnetic field. Our life is because of that, because it protects us from all these particles, energetic particles, and bad things which is coming from the rest of the interstellar medium. If you consider that dipole inside the Earth, that actually we still do not know precisely when it will flip, but it takes millions of years. Whereas in the sun, every 11 years, you have the polarity reversal. So now I need a theory which will have to explain this polarity reversal also. So what are the features of this butterfly diagram? One is these active regions which I have indicated. It will move towards equator. Poleward migration of the decayed diffuse field. Basically what is happening, the sunspot pairs, they appear, but with time, they also decay. So the strong fields go to the equator side, and the weaker field goes to the pole side, and polar reversal happens at the maximum of the cycle. So because that time the polar field has rushed to the pole, and then it has eaten up the existing polarity in the pole, and then the polarity reversal happens. All these properties has to be explained by a theory, which now I will explain in a very schematical way, not really a full-fledged mathematical theory. Of course, that mathematical theory exists, but it will be hard to explain it to all of you because it needs a lot of mathematical equations, which I will avoid. Basically, schematically, I can say this is a theory called a dynamo theory. It's very similar to the dynamo action what you see in your bicycle. You pedal the cycle, and this mechanical energy gets converted into electrical energy, and then you see your light glowing. So here, one form of energy has to be converted to another form of energy. That is the principle of a dynamo. So here also I will see how this cyclic process can be established. What happens is, sun has a poloidal field from north-south direction, as you can see. From the poloidal field, we have to generate a toroidal field. Toroid is nothing but a theta phi direction. You can think about the toroid, donuts. You are familiar with that, right? So the r theta poloidal plane, that field has to be converted into a toroidal field. So the toroidal field manifestation is the sunspots. So sunspots represents a toroidal field. I did not talk about one more element in terms of the solar rotation, which is namely the differential rotation. I mentioned that sun is rotating about its own axis, but I have not really explained that sun is also rotating differentially. What it means is that equator is rotating faster than the pole. This makes it life very complicated and difficult also. You think about yourself, your tummy is being stirred at a different rate, and your head is rotating at a slower rate. You can imagine what kind of stresses and stretching will be there inside your body. This is what happens inside the sun. So as is indicated here, so these are, suppose you start with a north-south oriented magnetic field lines. Magnetic field lines represent the connectivity of the two magnetic polarities. I hope you have come across this dipole. When you sprinkle iron fillings near a bar magnet, you see these iron fillings are oriented around certain directions, certain path they follow. The path they follow is called magnetic field lines. So here also we represent these as a magnetic field lines. And as you can see here, if the red arrow in the equatorial region is moving faster, with the smaller arrow in the polar region, and that will generate this kind of configuration after a while, and you get the toroidal field. So that's the sort of schematical representation of this. So because of the differential rotation, poloidal field generates the toroidal field, and it emerges into the form of an active region or sunspots pair. But what happens is, because of the decay of these active regions, one polarity, as I said, the plus ones are going towards equator, the negative ones are going to the pole. And what you see here again, my earlier story, that these negative ones are going to interact with the pre-existing polar field, which was pluses. So now this one minus will annihilate these one pluses, and eventually the minus will dominate and the polarity reversal will also happen. So that's a kind of story. But of course, there is some more, physical reasons why these, these kind of weaker field goes to the pole and so on, is explained by something called a meridional flow. What happens is, if this is the surface of the sun, this is the underneath, 30% of the convection zone. What is indicated here is like a conveyor belt. You are familiar with conveyor belt, right? So in the conveyor belt, what happens if you put an object, you see in the airport, when your bag arrives, the bag comes to you, you don't have to move. So here, this conveyor belt pulls these weaker field to the pole. And eventually, that conveyor belt actually takes this polar field to the base of the convection zone. So this is called the convection zone, and this is the base of the convection zone. And that field, which has been carried to the base of the convection zone, again gets converted to the toroidal field in the form of a sunspot in the next cycle. So this is the cyclic behavior. That's why this picture is important, that because of the convection, when the field is there to start with here in the base of the convection, so they come up because of this force called buoyancy. I indicated you by this explanation that a lighter tube will rise to the surface. It's basically the same thing. And then because of the differential rotation, it creates the tilt between the two sunspot pair, and they appear in the surface. And then because of the meridional flow, it is carried to the pole. Then you have the polarity reversal, and then again, that new polarity field is taken back to the base of the convection zone, and then this cyclic behavior happens. So this is the current understanding of the solar cycle. This is a complete story of the dynamo theory, what we know of today. I will just briefly explain. Skip this stuff, but what I also wanted to indicate to you, this kind of good amount of theoretical work is happening within India as well. There is a colleague of mine, Dipankar, in IISER, Kolkata, who was also a student in Bangalore many years back, a few years junior to me. And he has developed a beautiful dynamo core, which was originally, of course, done by Dipendu's supervisor and our teacher, Professor Arnab Raichaudhuri. The basic theory was developed in actually, early 90s, and now it has been matured into such kind of, beautiful simulations with more amount of physics and so on. So here again, these are experiments which we run in the computer. So I'm just again trying to give you a flavor how the research is done today. You need, people to observe. That means you record those observations. Then those observations has to be explained with the help of some physical theory. And that physical theory is developed again these days within the computer. And then the computer simulation gives you the time evolution of that theory, which explains different observational features as well. So this is again a sort of, demonstrations how things happen. Now I will just last 10 minutes, probably I will spend on where do you get all these data from. In India, we are really privileged to have this observatory in Kodaikanal, which has been looking at the sun for more than 100 years. Of course, there were Britishers who were there. There were famous discoveries done by British scientists who were the directors at those times. But post-independence, this institute was taken over by government, and this is what is actually Indian Institute of Astrophysics today. So we have been looking at the sunspots for more than 100 of years. But what has happened is these observations were taken from this small little telescope. This is the top portion of a small little auditorium here. If you can get, selected in any of the internship or schools in the IAA, you will be privileged to get lectures here for 2 weeks. I also lecture here in this. Our lab is there in the backside. This building is, you can imagine, more than 100 years old, because this telescope, which is sitting on the top of this tower, is observing the sun from 1904. Even today, we take a picture of the sun with this. But this is all manually done. We were taking images through photographic plates or films. Now the question is, how do you sort of work with these plates or films, which are more than 100 years of old? We have preserved all those films, and in more recent years, we have digitized them. So I've been, involved with this digitization program. It's been a mammoth exercise. We have, digitized, several of tens of thousands of plates. And this is a huge repository. As you can see, just the white light is 31,800 plates, which we have digitized. And these images are all available to the public domain through this website. The other interesting thing is from Kodaikanal, I did not talk about much today about other wavelengths. Essentially, when you take an image in different filters corresponding to different wavelength band, you are able to probe different layers of the atmosphere of the sun. I did not talk about different atmosphere of the sun today because I wanted to only focus on the sunspot, but these sunspots will have its signature in higher atmospheric layers as well. So here, for example, there is a collage here. This is a white light image. This is called, the calcium image, which forms in the chromosphere about, say, 1500 kilometers above the surface of the sun. And then this is called H alpha image. There is another filter, which is, typically, say, 1700 to 2000 kilometers. Within that range, you have this images of the solar atmosphere. You see certain magnetic features. They're called filaments and so on. I will not talk about it again today at length. You can also take images by blocking the solar disk, and you see certain features at the outside the limb. These are called prominences. These are nothing but, it's like a magnetic cloud floating in the atmosphere of the sun. These are also very important in terms of these huge explosions, which you see. They're called coronal mass ejections, and the space weather context, they are very, very important. So those are, again, very important data sources. What I wanted to just share with you is that these historical data, think about, people think that, this old plates, images have, it's lost its importance and so on. It's not true. If you can revive those important information, by a digitized medium, then it becomes it's a very valuable source. And actually, I can take this pride. Today, probably the Kodaikanal Digitized Archive is one of the best of its kind in the world. And people from all across the globe are using this data. Every other month, you will find top international, journal articles coming from the Kodaikanal data, because the data is available now in the digitized form. Otherwise, people would not have had access to the data. This is the calcium image, which we take from this, Kodaikanal for last 100 years. So what I'm just showing you here is, from though you have seen this butterfly diagram, and this is the 3D, visualization of the butterfly diagram also from the Kodaikanal. I didn't show you from the white light. That also is available, just published a few years back. And as you can see here again, these calcium features, which are directly corresponding to the places where the sunspots are, also resembles this butterfly diagram. So all these kind of work which we are doing now from the Kodaikanal Data Archive, this is a fantastic resource. If students are interested, we can play around with this. We can look at some small little project, even the rotation of the sun one can work. So there are a number of projects one can do. So I'm again encouraging you to look at this kind of archive. It's a unique opportunity for multi-wavelength study. I did not elaborate too much, but briefly, as I mentioned, that if you take images from different filters, you are able to, probe different heights of the atmosphere. That provides lots of, additional information as well. So Of course, as you can see, that this kind of work is not possible to be done without lots of bright young minds. This is also called my Dipu's gang. This is slightly older picture, and now this is the current picture. I have these many students who are working. Not all of them are working on Sunspots, though. Only one or two out of this gang. But I have lots more people with different projects, and Aditya is one of our mission for the future. We are all working on Aditya project as well. So thank you for your attention.
Thank you. Thank you very much, sir, for exploring the sunspots within 1 hour. And I can see the chat box. Number of questions are there. I invite the questions again. You can text the questions related to this talk in the chat box.
Okay.
I will take the questions one by one.
Okay.
I invite students.
Let me see where the chat box is. Otherwise, I will stop sharing and then maybe take the questions. It becomes slightly easier, probably.
We'll take from the YouTube viewers, sir.
Okay, yeah. So you have to, because I'm not looking at the YouTube, you have to just, help me out in.
First question is from Vanshika Agrawal from 9th standard. How do we know the polarity of the sunspots by just looking at it?
Oh, very good question. So you are absolutely right. If you just take a white light picture, you won't know. So that's again another big challenge what we have. Historical data do not have that polarity information at all. Once we have started regularly observing the magnetic field through this kind of, you have probably not heard, maybe Zeeman effect is a property which splits a spectral line if you are observing on a magnetic region. So using the concept of Zeeman effect, we have now been able to get the information about the magnetic field, and also through polarization properties and so on, we get the sense of the direction as well. You are absolutely right. This is the major problem what we have for historical data, that we do not have the polarity information. We can only guess that where there is this dark region on the white light image is a place where magnetic field is there, but the polarity information doesn't exist. That information we only have regularly from mid-70s. So one of the most challenging thing, or what we are doing, is going back to the history and creating this pseudo magnetogram through a lot of artificial intelligence and a lot of modelings and so on. So this is one of the most challenging task for us. And since you asked a question from class 9, it's fantastic, because we are just writing a paper for a very big journal to create this pseudo magnetograms. We don't have that information for the past century.
Next question is from 7th standard student. Sir, why don't the sunspots appear on the poles?
Okay, very good question again. So what happens is, I'm quite fascinated that you guys are asking quite very fundamental question actually. So as I indicated, that these sunspots seems to be getting birth in the base of the convection zone. So when they come up with the surface, they are dragged by this rotation of the sun, and because of the differential rotation of the sun. So there is something also called the Coriolis force. In a rotating file system, you have heard about centripetal force, centrifugal force, and so on. So because of these two, omega and r rotational motion, you have also something called a Coriolis force. So how fast this sunspot will come to the surface, that because of this buoyancy force, and how much it will be dragged by the Coriolis force, there is an interplay between this. In the case of the sun, this Coriolis force dominates. So while you are coming up, something is dragging you. So it cannot come to very high latitude. In fact, in the case of the sun, things do not come more than 40-45 degree at all latitude. Since you asked the question, now we have evidence for very strongly active stars, where the sunspots are actually, the sunspot what we are talking about today is mostly kilogauss strength, a few thousand gauss. If you have a sunspot which is of megagauss strength, which is now seen for some stars, there the star spots appear in the pole. because there the magnetic buoyancy force is much stronger, right? Because the field is much stronger, so the rotation is not able to pull it to the lower latitude. It pops up into the more closer to the pole. So to answer you, in the case of the sun, because of the drag or the rotation being stronger, the sunspots appear only up to 40-45 degree latitude. Whereas in other stars, we have now evidence that the star spots are possible to be seen in the polar region.
Next question is from 7th standard student only. Sir, where was the biggest sunspot was observed till now?
Okay, again.
And do they have some names?
Sorry?
Do they have some names?
Yes,
Sunspots?
yes. So as you can imagine, there is a evidence called Carrington, sunspot. As you can imagine, this was something around 1800. So there, of course, the detailed observations were not there. So there were only drawings available. So from that, it appears that seems to be our known recorded biggest sunspots. But again, since you asked this question, there are a lot of theoretical work happening now saying that if there are sunspots which are even bigger than the Carrington case, what would be the scenario? If there is a flare or big explosions coming of that sunspot, will that affect our atmosphere, the satellites and things like that? So there's a big story. These are called super flares coming out of this kind of very, very large sunspot. So we don't think that it will happen in near future, but if you look at thousands of years of probability, there is always some people work on that, whether there is a possibility of a super flare. So as far as we know, historically the Carrington one seems to be the largest. Yeah.
And this question, sir, I am asking you, one of the student has asked, how do we safely observe and capture pictures of sun and sunspots from home with backyard telescopes? Are we in an active or silent period of sunspots now? I think you tell them about the precautions, because
sure, absolutely, this is very, very important, and this is actually will relate me to also tell you something about eclipses. First of all, sun is a very bright object. You should never look at the sun directly or through a telescope or through a binocular or anything. No optical devices you should use to directly look at the sun, because even actually if you use an optical device, it's even more dangerous because it converges the light into a point. So always either you have to look at a projected image, or of course modern day your telescope is always fed with a camera, and that camera feeds your image into a computer or something. You can also use a pinhole camera, and from the pinhole camera, the image what you see at the surface, will give you a full disk image of the sun. So never look at the sun directly. In fact, even during the total eclipses, what happens is the solar intensity, reduces. What happens slowly, the solar disk get blocked during the totality. Only during the totality, when the solar disk is completely covered, one can look at the sun, without any filter or so. But that is only for a few seconds. So you have to be very, very careful when that happens and so on. So even under eclipse conditions or otherwise, never look at the sun directly or through even any optical device or images. The other part of the question is, now we are undergoing actually sunspot minimum. So we seems to have come out of the sunspot minimum, and we are seeing few sunspots which seems to be belonging to the new cycle. So we underwent a solar minima, and it appears now, just last few weeks, whatever sunspots are coming, they belong to the new cycle. So we are on the, again, rising phase of the solar cycle. But sunspot being there or not doesn't matter in terms of the total intensity. The total intensity of the sun is very, very high. A sunspot will only take 0.0001% of the intensity it will absorb. So don't think that being many sunspots on the surface of the sun, it is safe to look at the sun. No, please don't do that.
Next question. How does sunspot affect the size of sun?
It doesn't
Does
affect the size of the sun at all. There is something we are still debating whether with the with the long term change there is any variation of the solar diameter. Again, one thing you have to remember is this sun is not a spherical round solid object. It's actually a plasma blob. Plasma is a sort of a state of matter where it is a collection of particles and charges and ions and so on and so forth. So it's like a jelly, so you can think about the jelly. So but the variation in the diameter, still it is not an established fact. Even if it is there, it will be so tiny, we're still not able to measure it. So sunspot being there or not there doesn't affect the size of the sun. That's the answer.
temperature range of the sunspots?
Okay, that's a good question. So what happens is, normally the surface temperature of the sun is typically 6000 degree Kelvin, say. Since the sunspots are very strong magnetic field regions, they absorb certain amount of energy which is coming from underneath. And also there is another fact is the sunspots are very strong magnetic regions. So, I mean, if you are slightly higher up in your course, I can write down some equations and explain. But generally, what happens is, because of the presence of the magnetic field, there is something called a magnetic pressure. And so, inside the sunspot, there are two types of pressure. One is the plasma pressure and the magnetic pressure. So, there are two elements. Whereas outside the sunspot, there is no magnetic field, there is only plasma pressure. So to have a pressure balance, this plasma pressure inside the sunspot has to be lower. That directly implies that the temperature inside will be also lower. So typically there is always almost 1000 degree temperature difference between inside the sunspot and outside. So that will be your rough answer.
There are many questions, so I need to filter it out so that
Okay.
we can cover.
Yeah, because in my chat box I don't see, because I'm not in the YouTube. So
Yeah. Why there were no sunspots during those 5 years?
not 5 years, it was 50 years. Yeah. So this is something called a Maunder minimum, and now still we do not have a complete answer, but there are speculative research papers on that. One is that there is a possibility that there were sunspots, but they were very weak. So if they are very weak, then you can imagine 350 years back, the kind of telescope and observing facilities were there. They were not able to detect them. That is one possibility. Now the question would be why they will be weak. So now there is a speculation that, as I mentioned, that the solar cycle is maintained by few things. One is this differential rotation. The other is, of course, the convection and this meridional circulation, this conveyor belt, what we talked about, and so on. So it has to be that one of those parameters were changed, probably much less efficient as it should be. But then why it was so, also we do not know. But people have shown from the dynamo calculations that if those parameters are changed adequately, then you may have a situation where there will be only very few sunspots, or the sunspots will be very weak. So this is what so far people have been able to prove. Because at the end of the day, if you think about this dynamo thing, when you stop cycling, your light also stops glowing, right? So of course sun cannot stop rotating, so that but whether it slowed down for some reason for some period, that's again a very, very huge speculation. So this is a very, very open question, and we still do not understand. So maybe one of the research problem when you grow.
Is it also related to the explosions in sun?
Yeah, so the explosions on the outside surface of the sun is related to sunspots and its evolution the rotation. Actually, I did not talk about the sunspots also move on the surface of the sun. And it's just not always I was talking about two sunspot, but there are active regions where you could have 30, 40 sunspots together. So when you have 30, 40 sunspots, you can imagine a situation where there will be so much of interactions of these magnetic field, and that results into explosion. So explosions in the terms what I was talking about is mostly in the atmosphere of the sun, where the magnetic field interact with each other. And when the plasma, which is confined within the magnetic field, once the magnetic field snaps, you can imagine of a situation with these rubber bands, right? If rubber bands are thicker, and then if you start twisting them too much, and you cross each other, then the rubber band snaps. So if material is contained in the rubber band or these kind of tubes, they will spill out. So these huge spill out material is thrown into the interplanetary space. So that's the kind of flares or coronal mass ejection I was talking about.
Do they contribute to weather changes?
Okay, again a very very good question. There are two things. One is long-term change. So one of the reason why this Kodaikanal kind of long database is very very important is to understand over 100 years, where we could include say 9 cycles. If you have 11 year as a period, at least you have a reasonable amount of period over which you can also study our atmospheric changes. Because at the end of the day, what I mentioned is our presence here is because of the sun and its radiation. We consider that the solar radiation is constant, but actually it does change, and it does change by 0.1% with solar cycle. So if this 0.1% becomes 0.5, you can imagine that will have a big impact. In fact, since you asked the question, during the Maunder minimum period, when there were no sunspot observed, the Earth was extremely cold. Europe, the river Volga was frozen for 40 years. There were several tens of thousands of people died in Europe because of extreme cold conditions. So there is of course, direct impact of, if the solar radiation becomes drastically changed. And since we do not understand what exactly happened during the Maunder minimum, so you can find a causality that if there are no sunspots also, there is an effect on our climate. So this is what we study, and that's why a data like 100 years of Kodaikanal is very 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 important.
Said something about the Doppler magnetogram.
Okay, so that's a bit more technical. So these are called MDI. This is an instrument on solar and heliospheric observatory. So that can measure the magnetic field and also the direction. As I mentioned, it uses a property of the magnetic field line splitting. So you have to use a spectral line which is magnetically sensitive, and if you can observe that splitting of the line, you can get a measure about the strength of the magnetic field. And for the orientation of the magnetic field and all that, you also have to use the properties of the polarization. So combination of these, from this magnetic Doppler imager, it also measures the Doppler shifts of the spectral line, which will also allow you to produce some velocity Dopplergrams of the sun. But they're little technical in general, yeah.
There are a huge number of questions here in the chat box, so it will be difficult to cover each and every one. So I'm trying to filter it out, because some of the questions are something of informative kind.
Mm-hmm.
Students can get those answers from the Google.
Okay.
We'll take one more question, and then we'll stop.
Yeah, I'm okay with another 5-10 minutes if you think you.
Yeah, there are many. I need to sort it out.
Yeah, they can also write to me. I mean, they can write to.
Yeah, it will be a good thing if
you can get. Yeah, sure.
they want to know more about the temperature. of sunspots?
Okay. Um, so as I said, precisely at the surface of the sun, there is a temperature difference between the sunspot and the neighboring region because of this plasma pressure balance. And typically in the sunspot, again, it will depend on what is the strength of the magnetic field. If it is of the kilogauss in nature, the temperature will be much lower as compared to the surrounding. Now that is the surface one, but I did not talk about much about the atmosphere of the sun. Sun, essentially, since you asked this question, when you go away from, say, Earth, you go to the mountain, or if you come to Nainital, you will always find the temperature to be lower. And if you go further up, the temperature goes still lower. But in the case of the sun, it is opposite. You go higher up in the atmosphere, the temperature is very high. Actually, all the way, we call it a surface called corona, not the virus corona, but actually the virus corona name has come from solar coronal image from the total eclipse only. So in the corona, the temperature is millions of Kelvin. So if you are sitting on a sunspot and go high up in the atmosphere, again, the temperature will be higher as compared to the surrounding, but the numbers will be much, much different. So this is a different research problem called atmospheric heating problem of the sun, or the coronal heating problem. And there are different mechanisms what we understand now can explain this extra amount of heat generated there, or temperature higher in the upper atmosphere. That's another story. So I need full 1 hour to explain that.
True. Thank you very much, sir, for your kind patience for these questions. I hope this interaction will be fruitful for their development of astronomical world understanding and the development of the astronomical world. You can share your email ID with them so
Yeah,
that
sure.
they can
So you
directly.
can just make a Google search with my name. You will find my homepage also. It's Deepu at iiap.res.in or Deepu at the rate aries.res.in.
So I will text the email
Yes,
ID
yes,
in the
yes, yes.
chat
You can do
box so
that.
that you can directly contact
Perfect.
sir
Perfect.
with your questions.
Sure.
Well, thank you very much, sir, for your time,
My pleasure.
and would love to see you sometime at Bajaj Science Center. So please
Sure.
accept our invitation. After these pandemic days, would love to see you on our platform. And
I will
thank
love to come and meet the students, the bright students you have,
yeah,
whom I couldn't see today, but I
yeah,
would love to see them face to face and interact with them. I enjoy that. Yeah.
thank you very much, sir.
Welcome.
With this, we would like to end the session. Thank you very much.
Bye bye.